Okay, now welcome to this week's GOCC. We're very happy to have Nadia Lafreniere from Dartmouth, who is going to be telling us about or explaining how many times should you shuffle a deck of cards. Before I give the stage to her, I just want to remind everyone of the community statement for the seminar, which says that 1, we are all learning. 2, everyone has something to contribute. And 3, no one has all the answers. Okay, with that, I will give you the stage, Nadia.
Thanks, Sarah. Thanks to all the organizers and to all of you for being here. Maybe the first thing I want to say is that I'm not going to share my screen the whole time because I would like this chat to be pretty collaborative, and I'd like to see you and have you discussing as well. So that being said, feel free to interrupt. I'm not sure I'm going to be able to monitor the chat, but it's just say, hey, can I ask a question or something? And I will, of course, pay attention to that. And similarly, because I'm not going to share my screen the whole time, I wrote some notes, putting the link in the chat. They're kind of in the form of lecture notes, so don't read them. My goal is just to go over the content of this, and once in a while we'll show what's on my screen because there is something that I need to show you. On the first page of the notes, there's a permutation of 20, and I'm not going to read it to you out loud. I think it's going to be more helpful if I show it to you. But yeah, feel free to just take part in this chat because I don't want to be the only one talking today. All right. So that is the first thing I wanted to say. And then the second thing I wanted to say is basically try to give some answers, partial answers to the question, how many times should you shuffle a deck of cards? So here is a deck of cards, just like normal playing cards. And then on the other side, you see the famous cards, so heart, diamond, club, and spade. And my question is, well, this one has 52 cards, but in general, if we had n cards, how many times we should shuffle a deck of cards? And this is a problem that has been studied extensively by probabilists and a little bit by combinatorialists. And sometimes the answer is quite simple, but the process to get to that answer is very complicated, especially to people that are not probabilists, as I believe many of us are not. And I would like to give some maybe simpler answers to that. They're not quite the full answer, but sometimes we can get very, very good intuition just from the combinatorics. So from things that we actually know. And I remember much better when I have intuition. So this is why I want to share my intuition with you. So therefore, most of my talk is going to be about when a deck is not well shuffled enough. And basically just how we can find some lower bounds on what we call the mixing time, so the number of times you should shuffle, by just looking at permutation statistics. And I believe that this is something we're experts on, permutation statistics or permutations in general. And if we just look at that and without really looking at probability, we can already have a very good sense on when a deck of cards is not shuffled. Then I'm going to talk about, well, this is only part of the answer to say when it's not shuffled, but then how do we prove that it is shuffled? And this is a much, much harder question, but I'm just going to give maybe hints of how people tackle this question. I'm going to talk about when these things happen at the same time, so both the lower bound and the upper bound converge, and then maybe one piece of advice that I receive if you are ever interested in working in this field. It's actually probably one of my favorite pieces of advice ever, so I'm happy to share it with you. And anytime you have a question, I repeat it, feel free to interrupt and ask your question. So let me start, and I'm going to talk about what some probabilists call features and what I would call permutation statistics. So we can first talk about maybe some impossible permutations. And the first shuffling technique I'm going to introduce is also the first one that has been introduced historically to really talk about to really talk about card shuffling in this perspective, and it's random transposition. So I have a deck of cards, and I will pick 2 cards at random, any 2, let's say this one and that one, and I will swap them. Okay, you would never shuffle your deck of cards this way, right? It seems very bad, but let's say we have like 100 cars in a parking lot and we want to shuffle them for whatever reason. Moving them all by one spot is something that seems like impossible, but like maybe just like swapping 2 of them is doable. We only need 2 drivers for that, or 1 driver if you are willing to go multiple times. Anyway, it's doable. So the mathematical model for that is you pick 2 numbers between 1 and n at random, and you are allowed to repeat the numbers. So if you pick top card and then you pick also top card, it means that you swap the top card with itself, so you don't do anything. So you do this, choose 2 numbers at random, swap what's at these positions if the 2 numbers are different, and then you repeat several times. Okay, how many times? And that's going to be like the central question of this talk. You repeat several times, sure, how many? And the reason why I'm saying that is because this is actually how this project started. So at the Bell Labs, they were trying to generate some random permutations. They were doing exactly this technique. And for some reason, the algorithm was doing for permutations of n transpositions. But then the people started noticing that the permutations looked a little odd. And so we're going to look at some of the permutations together. The larger the permutation, the weirder it looks. The problem is that I don't want to show you permutations of 100 and just like stare at them, because I think we're going to run into some issues. So let me share with you some permutations of 20. Can you see my screen now? Good. So here we have 2 permutations of 20 that I generated using this algorithm. So I asked Sage, like, pick 2 numbers at random. If they're different, you swap what's at these positions and you repeat several times, and actually do it 20 times for permutations of 20. So I did that. I asked Sage, seems like the right thing to do. And then I want to look at these permutations. To me, they don't seem normal. Does anyone have some insight as why they are not like generic permutations? I guess I might give you some hint.
We have one comment in the chat saying that there are a lot of fixed points.
There are a lot of fixed points. That's exactly it. So if we look at the fixed points, I took notes. Oh yeah, here of what the fixed points are. We can look here. The first permutation, it has 10, 11, and 14 as a fixed point, and the second permutation has 2, 16, 18, and 19. And then, so this is with permutations of 20. I said I wouldn't want to do permutations of like 100, but I tried the same with like in my class to like, I showed some code to my students to convince them that this was a bad algorithm. And with permutations of 100, I was getting in average 12 fixed points. And sometimes I would get like 20, and sometimes I would only get 8. So this is a first. I'm going to stop sharing my screen because I want to see you again. This is a first thing that looks weird. So I don't know how familiar you are with permutation statistics in general and fixed points in particular, but there are a lot of fixed points. Maybe I could say that in average, the permutation typically has 1 fixed point. So that is the average. That is regardless of how large n is. And then if you want to be more precise on how many fixed points there are, the number of fixed points converge to a Poisson distribution with parameter 1, which means that like a third of the permutations have 0 fixed point, a third of the permutation have 1 fixed point, then like maybe 10% of the permutations have 2 fixed points, and then it just like decreases. And permutations of 100 with 18 fixed points, that's like very, very unlikely. And if I do this several times and I always get more than 10 fixed points, there's really something wrong, because it seems like I only get a small sample of the permutation, like permutations that have a lot of fixed points. So Mike that wrote in the chat that there were a lot of fixed points. Yes, this is something that was very unexpected here. So what that suggests is probably that this is not well shuffled. So why is it that? So if we do n transposition, like if we do a transposition, we swap 2 cards, and then these 2 cards can be anywhere. But if a card has never been picked in my n transpositions, it's for sure a fixed point. So if there are a lot of cards that have never been chosen, we have for sure a lot of fixed points. So how could we ensure that we will have enough fixed points? So like, let's say I shuffle k times, like how many cards won't be chosen? Or like, what is the k that I need to choose all the cards at least once, and then they can be anywhere? So this reminds me, and maybe you have seen that problem too before, of the coupon collector problem. So the coupon collector is kind of a problem for drawing with replacement, that says that asks what is the time necessary to collect all the coupons, which I think of, like, I don't know why they're called coupons. I would think of them as like Pokemon cards or like hockey player cards. That's the way I think of them, but the problem is called the coupon collector. So there is like a collection of Pokemon cards that says roughly how old I am. And we want to collect all of them. And we just like go into these machines that sell Pokemon cards. It gives us a card at random. Well, the original problem is like all the cards are equal, which I don't think is the case with Pokemon cards. Anyway, it gives us a card at random. And then the question is how many cards we will have to buy to have a full collection, or like how many cards we should expect to buy. And then turns out that this is not super complicated to compute. And the answer is roughly n log n plus a small number, but roughly n log n. So if we only do n transpositions, we pick 2n elements. And when n grows, this is pretty far from n log n. And that explains why we have so many fixed points. So this gives us a lower bound saying that if k is less than n log n over 2, then we have no hope of having few fixed points. And having no hopes of having few fixed points is bad. Like if we think that there are some permutations that are very, very unlikely, then it's not great, right? Oh, yeah. So, Dari, to your question, you can write a permutation as a product of at most n-1 transpositions. That doesn't mean that you will be able, if you take those transpositions at random, to generate all the permutations.
Yeah, it's kind of weird. You have to be strategic.
You have to be strategic. And when I pick 2 numbers at random, I'm not strategic at all. And that's exactly the game. The game is not to be strategic. We really want to have some randomness here.
Out of curiosity, does this difference kind of give us a rough idea of how many different ways there are to write the same permutation as different sets of transpositions? It should be roughly log n, because that's kind of the compactifying that's happening here, right?
I have no clue if this is
okay.
Like how this works. Yeah, it never occurred to me, and maybe it's because like I really have not really gave a good enough thought at this. But I would think that there's way more than log n ways to write some permutations. Maybe in average there are only like log n ways to write a permutation as a like reduced word, but I think that in general, or as a reduced transposition, but I think in general it's larger than that.
Okay.
Yeah. Yeah, so the coupon collector tells us that we should do this at least and again over 2 times. So this is again just at least, but it's a permutation statistics that we have noticed. And if we want our permutations, well, that statistic on permutation to be distributed the same way as on permutations in general, when we applied some number of transpositions, we should shuffle at least and log n over 2 times. It's actually a theorem from Persidakonis and Mehrdad Shashani from 1984 that the mixing time of the random transposition shuffle, so the number of times we should repeat that procedure, is of the order of 1/2 n log n, so like very close to 1/2 n log n. So if we do this 1/2 n log n times, so like I don't remember quite well, but it's like something like 200 times, we're good. I mean, you've seen how long it took me to just like swap 2 cards, but if we have a row of 100 cards, it gives us the number of hours we should pay our staff to do it, roughly. Not that I think you should do that, but anyway. So that is for the first shuffling technique. And then I'm going to move on to other techniques in which I'm going to talk about some other shuffling techniques, but also other features, so other permutation statistics or other ways to see that it's not well shuffled. So the next method I want to talk about is top to random. And top to random, the name is pretty explicit again. So I have a deck, I take the top card and I insert it anywhere at random. And then I will do this several times. And my question again is how many times I should do this? So here, one thing we might want to notice, so like now we're looking for a feature. What is our feature that is gonna be not so well shuffled? And I guess I should have generated permutations again with this technique to like really exhibit the feature, but I totally forgot to do it. But I think the reason why I didn't do it is because it's something that I can easily do with my deck of cards. So let me grab a new deck of cards. So if you take a new deck of cards, it's always in the same order. So if I show it to my screen, we have ace, 2, 3, 4, 5, 6, 7. And let me just take the spades because it's going to be just like enough cards anyway to see something. So I'm going to do top to random, and I repeat top to random. I will repeat top to random. And you tell me when I should stop. Maybe I should do it like n times. I think it's now 5. Then I'm going to do 6, 7, 8, 9, 10, 11, 12, 13. Okay, that's 13 times. And if we look at it, okay, what do we have? What I see here is a bunch of, okay, 2, 3. There are a couple of cards that are in the same relative order as they were. And just as a reminder, we have like ace, 2, 3 from the bottom, and ace, 2, 3 are still in the same order, which bothers me because it was actually impossible to have ace, 2, and 3 in a different order. And this is the problem. And I'm going to explain to you why. So when I take the top card and reinsert it anywhere, the only card that goes down is the top card. The other one are either like not moving or they're going up.
Right.
So which means that the cards that are not reinserted are staying in the same relative order. So of course, if I do it only once, you'll think it's silly, like I only moved one card. So of course, the n-1 other cards are in the same order, but until every card has been picked, then most cards are, there are cards that are in the same relative order. So like, I'm gonna do this again, this time with a diamond, because that's the next suit I have on hand. What I'm gonna do is I'm gonna pick a bookmark, just a bookmark, and I'll put it just above the ace of diamond. So I have only one card that is below the bookmark. If I insert my card above the bookmark, it's like not recording anything. But if I insert my card below the bookmark, it has equal chance of being above the ace or below the ace. So I put it in any position. And then for the next card, it has equal chances of being above the ace or below the ace. And it also has equal chance to be above, well, to be above the ace or between the ace and the queen or below the queen, actually.
Right.
So I insert it anywhere. So what's below the bookmark is always perfectly well shuffled. And what's above it, like some cards haven't been picked yet. So because these cards haven't been picked yet, they are in the same relative order. So this is bad. And I might insert some cards in between here, but anyway, there are still cards that haven't been picked yet. So this is not great. So as long as the bookmark doesn't reach the top, there are some cards that will be in the same relative order. So it's bad. So they will be above the cards that were originally below the bookmark, like the ace. So the ace was always below the bookmark. So the cards that haven't been picked yet are always above. So
when
yeah.
you move, do you need to shuffle the ace? Yeah, so would you need to shuffle the ace in order to finally get a well shuffled deck?
No, so if the ace is like the only card you wouldn't have to shuffle.
Okay.
Because like everything can be anywhere relative to the ace.
Sure.
But I cannot
You need
put
to shuffle the
two cards.
king, but maybe many times.
Yeah. Yeah. You cannot have two cards below your bookmark for sure.
Mhm.
But one card is fine. And then it's actually give us a like as long as there are still cards that are above the bookmark, my deck is not well shuffled. So my question is, how many times should I repeat that for the bookmark to reach the top? And this is another occurrence of the coupon collector problem. Because if you look at so like here, I don't pick my card at random, but if you think of the opposite shuffle, random to top, you pick any card at random and you put it on top. All the cards that haven't been picked are in the same relative order. And then it will be perfectly shuffled once all the cards have been picked. So once we have achieved the coupon collector problem, which tells us, and log n is the number of times we should do that. And again, this is a theorem by Diaconis, Phil, and Pittman from 1992, that it takes n log n plus n repetitions of the top to random shuffle to get close to the uniform distribution. So our combinatorial intuition only tells us that n log n will be enough, but it's actually just n log n plus n, and then we're good. So it's great. It's a pretty nice theorem. One of my favorite way of shuffling, even though I cannot really do that when I'm playing with people, because like no one wants to look at me just like shuffling cards forever. N log n is pretty large, so it's a little too long to actually do with people. A similar technique that I want to talk about, and Dari is here, so he might be pleased to listen to me talking about this. Dari and I recently studied another shuffling technique that is similar to top to random, but might look more random. And I actually would like to, I was wondering if it was more random or less random than random to top or top to random. They're the same, kind of. So what is random to below? You pick a card uniformly at random, remove it, and reinsert it anywhere below. So it can be reinserted at the same position, but it cannot go above. So it's kind of like you pick a card at random, you put aside everything that is on top, perform top to random on what's left, and then put back what was on top. So if you pick the bottom card, you have to reinsert it there. If you pick the top card, you just apply top to random. And in between, well, it varies on how close it is to the bottom or how close it is to the top. So yeah, when I started talking to people about that, some people were like, oh, that's going to be faster than top to random because it's like more random. Because you don't pick the top card, you pick a card at random, it should be faster. And I wasn't sure. I was like, well, it also looks to me lazier. So lazy for a probabilist or for Markov chains means that you don't move. So for this is like any step that I don't do anything. So with top to random is I take the top card and reinsert it on top. With random transposition is I pick twice the same position, so I don't swap any card. And then with random to below can be that I pick the bottom card, I have to reinsert it there, or the one just above, and I have probably 1/2 of reinserting it where it was. Or it can also be that I pick the top card and I have probably 1/n of reinserting it on top. So this, to me, it is much lazier than top to random because it happens more often that we don't do anything. So then when we decided to like finally tackle this problem of finding how long we should shuffle, we did the same technique of the bookmark. The computations were harder, but again, as long as the bookmark is here, for example, while the cards that are above have to stay, like they cannot be below the card that was initially at the bottom. So we do this until the bookmark reaches the top, and we find that it takes n log n plus n log n. So it's a small factor that we're adding. And if you know Dari and you wonder how he got interested in something like mixing time of shuffling a deck of cards, that was not the original problem. The original problem was not about the mixing time, it was about the eigenvalues. So there's a way when we have card shuffling technique that we can associate it to a matrix, just like we have a Markov chain and we look at a transition matrix, and then we wanted to compute the eigenvalues of that. But these are very large matrices, like 52 factorial by 52 factorial. So computing the eigenvalues is not something we can do with like for a deck of cards. And here we were looking at n factorial by n factorial. So like really forget about computing the eigenvalues in any naive way. But the eigenvalues are beautiful. They are rational, they're positive, they can be explained by simple combinatorial objects. So they're really, really cool. But we wanted to know what they were. One application of knowing the eigenvalues is often to compute the mixing time, but not in that case because the transition matrix was not symmetric. So it was like a little useless, let's say, to find the eigenvalues. But when I see that, like when I have a matrix and I can explain combinatorially the eigenvalues, I just think it is beautiful. And the way we proved it has some beautiful math. So it's kind of really cool. And then as a complement to this project where we say, well, the eigenvalues are useless, we cannot compute the mixing time, we computed the mixing time using a completely different way. So yeah, just a side idea on like how we can, well, a side comment on the fact that we can use these ideas for like shuffling techniques that haven't been explored yet. And even sometimes the computation of the mixing time is pretty simple. Yeah, so that's what I wanted to say about top to random. Yeah, and positive integers are their own reward. That's exactly what I needed. I'm like, oh my God. Well, they were not integers. They were like rational because the probability of choosing a card like is different for each. So, but they were like rationals that we could explain. So yes, positive integers, just that, it made my day, it made my year. Anyway, we have our own reasons to be excited about that. But I know that for many people, the only thing they care is like how long we should repeat that process. Anyway, that brings me to the most famous shuffling method, if I dare, which is the riffle shuffle. So what is a riffle shuffle? I take a deck of cards, just still the same deck, break it into 2 smaller decks, and then I will interlace the cards from each end, like doing this. Well, not this, but anyway, I've probably seen it. You know what I mean? That's take 2. Okay, it's easier if I do it on a table, but unfortunately my camera is not on a table, so it looks whatever. So what I do is I cut the deck roughly in half. So if we wanted to model that, we would say we cut it in half according to a binomial distribution. Well, we cut it roughly in half. So there's like maybe 12% chance of like having it exactly in half, but it can be like 24, 28 cards, it's fine. And then we interlace the cards from each end, like dropping the cards according to the number of cards I have in each end. And then I repeat that several times. But again, my question is how many? we're combinatorialists. Like if I tell you, oh, several, it doesn't mean anything. You're like, okay, it's finitely many, but like, how many is that? So here, again, we are looking for some permutation statistic, like some feature, like distinguishing statistic. And here I can tell you what that permutation statistic is the rising sequences. So what is a rising sequence in a permutation? So a rising sequence is the cards, like just a sequence where it's a sequence. Oh yeah, it's a sequence. For example, here I have the 6 of spade, and then I'm going to be looking for the 7 of spade, and I'm not going to stop until I find it. And then if it's earlier in the sequence, that's all for my rising sequence. So I'm going to give you an example, and here I think I would like to show my screen again. Share screen. Can you see it? Okay, so here I have, so that's a rising sequence, and here I have a permutation 5, 4, 6, 2, 1, 9, 3, 7, 8. Anyway, so I have, for example, 1. If I start at 1, I read to the right, there's nothing. I'm looking for 2 and I don't find it. So 1 is in its own rising sequence. And then I have 2, 3. So that's another rising sequence because 4 doesn't appear to the right of 3. Then I have 4. And again, 5 is to the left, so I stop there. Then I have 5, 6, 7, 8. So that's a longer rising sequence. It has length 4. But then at 8, I reach the end of the permutation and have to go back, and then I read 9. So here my rising sequences are 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, how many rising sequences are there in a permutation? You might not have seen rising sequences before, but I think you might have seen the rising sequences in the inverse. So why would you have seen rising sequences in the inverse? Because they are run. So if here I write the inverse of 5, 4, 6, 2, 1, 9, 3, 7, 8, I get 5, 4, 7, 2, 1, 3, 8, 9, 6. And then looking at this, because those are increasing, they're like not only increasing, but we're looking for the neighbors in the alphabet, which means that they're going to be increasing runs in the inverse. And the runs are just consecutive increasing sequences. So for example, 5, well, 4 is decreasing, so I stop here. 4, 7, then I have to decrease to get to 2, so I stop here. 2 is in its own because I would have to decrease again to get to 1. Then 1, 3, 8, 9 is increasing, and 6 is increasing by itself. And if you look at this, well, 1 was alone, and then 2, 3 were together. We have an increasing sequence of, we have a run of length 2. 4 was alone, we have a run of length 1. Then we had a rising sequence of length 4. We have a run of length 4. So it's really the same kind of thing. And then runs are separated with descents. So in between each run, what marks the end of a run is when I have a descent. So you might not know how to compute rising sequences, but you probably know how to compute descents or know what's the average number of descents. So you have n-1 possibility in total for where you can put your descents, and each descent will occur with probably 1/2. So the average number of descents is n-1/2. And there's one more run than the number of descents because the descents is what separates 2 runs, and we start with a run. So there's one more than n-1/2 runs, which means n+1/2. And that's the number of rising sequences. Okay, I'm gonna stop sharing my screen. So in average, we have n+1/2 rising sequences, which means that in our deck of 52 cards, we should expect like 26 or 27. However, when I do the riffle shuffle, I take half the cards in my left hand, half the cards in my right hand. The cards that are in my left hand are going to stay in the same relative order. Like I'm not shuffling them at all. Same thing with the cards in my right hand. So if I do the riffle shuffle once, I have at most 2 rising sequences. still very far from 26 or 27. And then if I do the riffle shuffle twice, I have at most 4 rising sequences. And if I do it 3 times, I have at most 8 rising sequences. But even 3 times, we're still very, very far from 26 or 27. And if we want to push it a little further, if we want to look for the permutation n minus 1, n minus 2, n minus 3, the decreasing permutation, like the one that goes from n all the way to 1, this one has 52 rising sequences. So we should, if we want all the permutations to be possible, we should aim for at most n rising sequences. Okay, so when does that happen? Well, we need that if we shuffle k times, we will have at most 2 to the k rising sequences. So we want 2 to the k to be greater than n, which means that k has to be greater than log n in base 2. Okay, well, that's already a good start. We have like a number this time, so k has to be greater than log n. That doesn't tell the whole story, so that is for every permutation to be possible. That's already a good start. It doesn't mean that all the permutations are equally likely, but it gives us a very good intuition. The first thing it tells us is that if you play cards with your friends and you do the riffle shuffle, you would have to do it at least 6 times to have all the permutations, for all the permutations to be possible. So it's probably more than what you do anyway. And then it's a theorem, again, from Bayer and Diaconis from 1992, that it takes 3/2 log n repetitions of the riffle shuffle to get close to the uniform distribution. So log n isn't like the whole story, but it gives us a good order of magnitude on like what is needed. And this is actually like 3/2 log n if we get more precise. Okay, so now we have 3 shuffling techniques: random transpositions, top to random or random to below, and riffle shuffle with their feature. So for random transpositions, our feature was a fixed points. For top to random, our feature was the order of the bottom cards. For the riffle shuffle, our feature is the rising sequences. But then there are some shuffling techniques for which I don't know what the feature is. I'm going to tell you about one of these, and this one is finally solved for the mixing times. We still don't know what the feature is, but the mixing time has been open for was open for like 25 years. So it was not an easy problem, even though it looks very similar to the other shuffles that I introduced you today. So here I have my deck of cards. I'm going to apply random to random. So random to random means I pick a card at random, move it elsewhere at random. And I see some people here that have done some work on random to random. I see Dari, I see Sarah. I myself have done some work on it. If Dari or Sarah, you have any insight on what the feature is, I'd love to hear about that. But really, it's kind of a puzzle to me. Like, what is the thing that is preserved in the permutations? Dari says he has tried to do some work on random to random. Yeah, I guess I could say the same about me, but I ended up doing some generalization of random to random. So it's some kind of work. But yeah, so what do we do when we don't have these features? So here it's a theorem that if we do random to random, it takes 3/2 and log n times to get to the uniform distribution. So that's more than many techniques, but like less than top to random, for example. So to the question, is it faster or slower than top to random? Random to random would be more random, like it takes only 3/2 and log n and not n log n times to get to the uniform distribution. Like how is that a theorem? Like how could they get that if there was no feature, if there was like no combinatorial things we could track? So the people that have done that, Megan Bertshine and Evita Nestoridi, are like they know some combinatorics, but they're mostly probabilists. And then they use some probability techniques. So I'm going to talk about some probability techniques and upper bounds in general, because so far I've only talked to you about lower bounds. So how do we get an upper bound? Like the theorems that I gave you are very different from the things I told you they were. Like I was like, oh, with the feature, we have that it's at least that many times. And with the feature, we have that it's at least that many times. And then I was like, oh, theorem, it is exactly that many times. So how do we get that? So there are two ways, but before, well, there are multiple other ways, but there are like two ways I want to talk about. But before that, I just want to say that showing that something is not random is hard in general, because like I cannot look at my deck and say like, oh, this is not random. Because if I look at my deck first, I know exactly what the order is now. So like I ruined it. But also because seeing that something is random, like how do you know that all of the other outcomes were likely if you only see one outcome? But sometimes you can show that something is not random. For example, what I did with random transpositions, I generated a bunch of permutations of 100, and then I counted the average number of fixed points, and I was like, hey, this is wrong. But showing that something is random is even harder, because I know, maybe, okay, I know that the distribution of fixed points is okay, but what tells me that there's no other feature? So it is a problem. So there are several techniques that exist, and I want to talk about two of them. The first is strong stationary time, and I claim that you've seen a strong stationary time about like 20 minutes ago when I talked about top to random. So top to random, I said whenever like whatever is under the bookmark is perfectly well shuffled. And then when the bookmark hits the top, I know my deck is perfectly well shuffled. So stationary time in general is a time at which you know that you have reached the uniform distribution. In general, we don't reach a uniform distribution, we only approach it. But with a stationary time, we know we have reached it. And with top to random, we know that whenever the bookmark hits the top, we have reached a perfectly the uniform distribution. This is rare, and this is probably one of the reasons why I love top to random so much, is because it's one of the few shuffles that is actually truly random. Not that it matters at that point. Like if you shuffle long enough, you always get close enough to random that really we don't care. But with this one, we actually get there. But in general, stationary time are not known or very hard to keep track of for card shuffling. So the main technique that is used, and it's used both for upper bounds and lower bounds, is the total variation distance. So what is the total variation distance? It's a distance between two probability distribution. And in our case, we'll have the probability distribution, so like the probability that we get one specific permutation, for example, after we do the shuffle k times. That's going to be one of our two distributions. The other distribution we'll have is the uniform distribution, because this is what we mean by well shuffled. And then we will measure the distance between these two distributions. So how do we do that? So maybe the outcome of that, like the distance itself is a number ranging from 0 to 1. And just as with any distance, if you have that mu and nu are at distance 0 apart from each other, well, they are the same. And then if they're at distance 1, which is the maximum, they are very, very different. So before we shuffle our deck of cards, we are at distance 1. And then once we're well shuffled, we're at distance 0. So what is that distance? Is we'll take all the permutations, and for each permutation, we will take the probability of being there after K shuffle of our shuffling technique, and we'll compare that to 1 over n factorial, which is the probability for the uniform distribution. We'll take the absolute value of the difference, and we'll sum that over all the probability and divide by 2 to get a number between 0 and 1. So, of course, we cannot, like, if we have 52 factorial permutations, we cannot just, like, naively compute the total variation distance, because we would have to compute something for 52 factorial permutations. But sometimes we can, like, with the example of the riffle shuffle, we can compute the number of rising sequences, and then for a permutation having that many rising sequences, we will get that number for the total variation distance, and then it's like something we can solve. But in general, it's hard to compute exactly the total variation distance. There are some bounds that are known, like how we can get some bounds, and one of the main techniques for that is using the eigenvalues, and this is why I said that people were interested in getting the eigenvalues of card shuffling techniques. But then I said, we have a distance going from 1 to 0. 0 is perfectly well shuffled, and 1 is like not shuffled at all. But when do we consider it to be well shuffled? I would say like when it goes below some threshold, usually 1/2. The threshold has to be lower than 1/2, but when it gets to 1/2, we say that the deck is close enough to uniform. We could choose other thresholds, but it usually doesn't really matter. And I'm going to get to that point. But maybe 2 comments I can give before that is that usually the total variation distance is hard to compute. So that's like one major problem. But also the other thing I want to say is that there are distances, like other distances and probability distributions that are easier to compute, like the separation distance. They don't give quite the same information, but they give other information that can be complementary. Okay, now I'm going to share my screen again because I want to show you what happens with the total variation distance for the ripple shuffle. Can you see it? Okay, so here is the graph for the total variation distance for the riffle shuffle after K riffle shuffle. And we see that it, for a very long time, like the first 5 times, it is very close to 1. And I said that, you know, until like we have the first 4 times, for example, or even like the first 5 times, well, let's say just the first 4 times, I have at most 16 rising sequences. So most permutations are impossible, meaning that we're very, very close to have 1 as a total variation distance. And then I start putting in some more rising sequences. After 5 shuffle, it is like 0.9. So still very high, but like less high. And then it drops sharply between like 5 and 8 shuffles, from 0.95 to like 0.1. So we know that this is where the shuffle happens. So regardless of what threshold I choose, if it's like 1/2 or 1/3 or 1/4 or 1/e or whatever the number you choose, it always happens in this window. So this is a phenomenon called the cutoff phenomenon, which is a sharp drop in the distance between probability distributions. And it is very interesting. Like we know that all the mixing happens at this time in like some short window of time. So it doesn't like gradually go down and then we can say, oh, well, if we choose this threshold, this will be enough. It's actually whatever the threshold we choose, they're all going to be equally good. So when we have cutoff, typically the distance stays at 1 for a long time, and then we have a sharp drop, like doubly exponential, roughly. So very, very sharp drop that happens during our cutoff window, and then it goes like very low, the distance, and then we have an exponential decrease for whatever is left, but that's just the tail. Really, like the mixing has happened. So we don't need to be very precise as to when like after how many shuffle precisely, because between shuffling 8 times and shuffling 10 times, it won't really make a difference. But we really need to be in that window or past that window. We cannot be before that window because that means no mixing has happened yet, roughly. So that leads me to my last slide. And I guess I have like 1 minute. Oh, maybe I can say something about cutoff. We don't know when cutoff happens in general. And cutoff is hard to prove. It's like really, that's not a combinatorics thing. That's a probability thing, really. So I don't know of any card shuffling technique that for which there is no cutoff, for which we have proven that there's no cutoff. So I'd say in general, card shuffling is kind of a global process, so it satisfies cutoff. But it's a very sensitive process, so sometimes even changing like small factors in the probability can break cutoff. And it is an open problem to say if we can predict cutoff without having to explicitly compute the distance between 2 probability distributions. And that leads me to my piece of advice that I said I received. I actually received it from Percy Diaconis, which is like the father of all these like shuffling stuff. And one thing that he said in the talk is that, I mean, there are many things we can compute, and many of these things are really, really hard. But what matters is not what metric you use or like how you got to that number. What matters is if you can say anything. So don't bother about the metric. And just if you can't say anything, say it. Like if you can have some partial answer, this is exactly what we would like to hear about. So like, don't focus too much on what techniques you're using or what, like if you use the separation distance or the total variation distance or other distances. What we want is just like any part of the answer, because this is a big story, it's still going on, and we could take any piece of the story. So that's all I have to say, talking about sharing stories. If you have anything to say, I'd love to hear it now.
Let's give Nadia a round of applause. All right, yeah. So let's open the stage to questions.
I was curious, why doesn't the bookmark method work for random to random?
My question is, where would you put the bookmark? Because
Yes.
what we have with top to random or with random to below is that there is only one card that is going down and no other card is going down. When we do random to random, if I pick one card and I insert it above, all these cards in between are going down.
Right.
So because it's like two-way, we don't have the same thing. And I was talking with my PhD advisor, Franco Saliola, who find all the eigenvalues for random to random. And he said to him, random to below was kind of more general than random to random, so it should be harder. And I'm like, well, random to random is just different, because, there are things that are much harder, like the mixing time. Random to below, it was fairly simple because we have the bookmark technique. With random to random, there's no feature. So the only way to get the mixing time was to use a total variation distance, and to find a total variation distance, we needed the eigenvalue, and just getting this was very complicated. So yeah, it's if you have any ideas for features that we could try for random to random, I'd love to hear about this.
So is there some kind of theoretical claim to the fact that there is no bookmark or other stopping time method, or is it just nobody has found one?
Nobody has found one, at least that I know of. It is not impossible that there exists one. Yeah. I see that Seth put something in the chat. I don't know what that is.
Oh, yeah. Hello. I
Hi.
put in the chat a link to Wikipedia's article on the Kullback-Leibler distance or divergence, which is used a lot in max entropy, maximum entropy studies of information for distance, a non-symmetric distance between probability distributions. So I'm wondering if you have seen any connections to your work of that as one of many, as I see, distribution metrics.
I didn't talk at all about entropy, but that's like definitely another way that people can show either cutoff or mixing time, but this is a whole different set of techniques that I don't know anything about entropy. So I should probably learn about it, but it's definitely something that is less combinatorial and more used by probabilists. And I tried to read some papers that were talking about entropy, and I was like, oh, this is really not, like, I would have to dedicate so much time to understand them. So I didn't really look at that. So maybe I would like just walk into that Kullback-Leibler divergence as well if I would know more about entropy, but I haven't much.
Roughly, it's a kind of relative entropy.
Okay.
You see the formula,
Yeah, I'm not aware of that at all. Oh, when is this book coming out?
Yeah, nobody knows. I've only heard about it a couple of days ago.
It says June or July in the chat.
So I have seen a previous version of this book, but it was a long time ago, and the person that showed it to me told me that it would appear soon back then. So I'm really looking forward to reading that book, though. It's kind of the book I was dreaming of when I was in grad school. So if you're interested in this type of math, the mathematics of shuffling cards is something you should look into.
So I've got a question, and this is kind of unfair because the question's coming from a sketched picture. But you put kind of, in order to represent the cutoff times, you kind of put an estimate, or maybe this is an actual graph of the cutoff time or the variation distance for riffle shuffles.
Yeah.
And right, so we see 6 and 7 labeled on this graph.
That's for 52 cards.
Right, so 52 cards, 6, we've just barely gotten every possible permutation. And just looking at this graph, it looks like even for 5, we're still in the cutoff window.
Well, so for 5, we're at like 0.95. So it's like not, we're in the cutoff window because this is where it started happening.
Okay.
But like we're really at the beginning of the cutoff. Like we cannot really say that the mixing has happened. There is, I mean, it's not, okay. So total variation and cutoff is also a phenomenon that depends on what metric you use. So this is the total variation cutoff that I showed here. There is a game that has been designed by one of my colleagues here at Dartmouth, Peter Doyle, to show that 7 shuffles were not enough. And the game, he calls it New Age Solitaire. So you have a deck of 52 cards and say, I want to play with you. I'm going to say that I need to find a rising sequence from 1 to 26. And you have to find a decreasing, well, like not like the inverse of a rising sequence, I guess, like a falling sequence from 27 to 52. So I'm gonna perfectly shuffle my deck of cards with like 7 shuffles, and then we'll play that game. And with probably 3/4, I will win. So this is not a perfectly shuffled deck of cards, because if it was perfectly shuffled, then there's no way I would win with probably 3/4. It would be a fair game, so I would win with probably 1/2.
I would be very interested for that reference, because I independently discovered that 6 shuffles was what you needed to get to all permutations. And I was very surprised then that 7 shuffles was sufficient. I was like, we need 1 shuffle more than getting to all permutations. But apparently the paper, the thing you quoted, 3/2 login is like 8.5 for whatever metric that paper was using.
So the n log n is like not quite 7, but n log n is like when n tends to infinite, it tends to n log n and be like more precise for a 52. But for the reference of the game that I was talking about,
yes.
So there is a like easier explanation than the paper. I don't know if there's actually a paper, but I know that there's an easy explanation in a textbook, the textbook that I'm using for my probability course. So, oops, just want to copy the link. So in this textbook, I think section 3.3 is about card shuffling. Anyway, the section about card shuffling, it explains this new age solitaire. And yeah.
Okay, yeah, that's very interesting. The place I ran into card shuffling is I work with Hopf monoids and Hopf algebras, and it turns out that the dual of the Hopf monoid on linear orders, co-product exactly replicates cutting a deck, and product replicates shuffling a deck.
Yes, and some people have done a lot of work using Hopf monoid techniques or Hopf algebra techniques. Like Amy Pang has a lot of work on card shuffling and Hopf algebra. Jerry, maybe you do? I don't know. I think you do.
Never very explicitly. I think I've simplified some of her proofs, but I never wrote about it.
Okay. Anyway, so you might want to talk to Dari about this. That's my point.
Okay.
Because he's also interested in that.
Yeah, but don't talk to me about the mixing times. This is not my part.
Sure.
Yeah, I'm wondering in the properties of the permutation that are used to define the quantity nu in the variation distance. What property ensures that the distance turns out to be less than or equal to 1?
So this works for if you take any two probability distributions, because probability distributions sum up to 1. If you take the absolute value of the difference between, like you sum the absolute value of the difference, you won't ever get anything that is higher than 1, because we divide by 2. So otherwise you wouldn't get anything that is higher than 2.
Okay, so I don't quite understand then the origin of the quantity nu that depends on the shuffle.
So
Is
nu
that a
is the
probability?
probability, it's a probability distribution after repeating the shuffle like k times.
Okay,
So the probability of getting, for example, the identity permutation, or the probability of getting the reverse permutation, or probability of getting any specific permutation.
okay, so nu of a permutation is the probability that the shuffle produces that permutation. Okay,
Yes.
good, I see. Okay.
And then if you sum over all permutations, well, if you sum over all outcomes, you get probability 1.
Yeah, so if it were Kubler-Lieblich distance, what would happen is roughly the difference would be replaced by one of the probabilities times the difference of the logs
Mhm.
of the two probabilities. And so it's non-symmetric, but that's the difference between your formula and the Kubler-Lieblich formula.
I thought this talk would explain. I thought those questions would tell me finally how to pronounce Kullback-Leibler, but now I've heard like 3 different pronunciations.
I won't vouch for my pronunciation.
How do you spell it? Someone write in the chat.
The way
Okay,
for
cool.
a pointer, a pointer to the subject that uses this stuff is that it's called information geometry.
Hmm.
It's like it's like the geometry, like Riemannian geometry based upon a metric. But what's peculiar about it is that, and which doesn't really matter for the geometry, that the metric is not symmetric, but it's just as good.
Yeah, I think Mark's right. Let's end the recording.